Well, good afternoon, ladies and gentlemen. Welcome to another in our series of i4energy seminars. This is the second of this semester, and this is about the third or fourth semester that we've been doing these talks. It's a pleasure to see you here, and I'd like to especially welcome our viewers on the internet, our sister CITRIS campuses at UC Davis, Merced, and Santa Cruz. And I would like to acknowledge and thank my colleague Gay Migny, sitting in the front row here, who has helped put together this program and is a co-sponsor of this event. I don't think that there are any other particular seminars or announcements that I need to bring up right now, and so I'm going to start right in by introducing today's speaker. Professor Alexandra von Meier, also known as Sasha, is a research coordinator at the California Institute of Energy and Environment, where Gay Migny, my colleague, is employed. She is a professor of energy management and design in the Department of Environmental Studies and Planning at Sonoma State University. She has studied and published on diverse aspects of energy technology, including electric power distribution, photovoltaics, and other related topics. Her research at CIEE focuses on the integration of intermittent and distributed generation in the electric grid, hence the topic today of the challenges that one could encounter in that process. She's the author of a seminal textbook, which I've read twice, and I recommend it highly, called Electronic Power Systems. I think, Sasha, you're going to be selling copies of these in the lobby after the meeting. Is that correct? No.
I didn't think ahead.
It's an opportunity that you could have taken advantage of. Professor von Meier received her PhD in Energy and Resources here at UC Berkeley and her BA in Physics from the University of California here at Berkeley as well. She was a postdoctoral fellow here in electrical and nuclear engineering departments, and she was a lecturer in energy and resources. So let us not delay anymore. Let's give our standard and enthusiastic welcome to Professor von Meier.
Thank you, Gary. Thank you so much. How can you hear me okay? The sound is all right? Great. Okay. So I thought the title actually sounded a little formal and unwieldy, but it is what I'm talking about. Now, I noticed about 8 or 10 of you were here on Tuesday in this very room and saw this very slide. I apologize. There's like a couple of slides that are the same, but the rest of the talk is different. The fundamental challenge of integrating renewable resources in the electric grid is the obvious fact that you can't get renewable energy when you want it and where you want it all the time. The legacy electric power system that's in place was simply not built and designed to accommodate the kind of energy that's intermittent and that's located in places that were different than the places that were convenient for fossil fuel-based power generation. Now, as recently as 10 years ago, people may have said, you know, this is a showstopper. We just can't do renewables. It's an insolvable problem. They're too unpredictable, too intermittent. It's too awkward. It can't be done. I think we've come to the point of recognizing that, well, it's not a trivial problem, but it's likely solvable. It's not easy. And it really is a difficult but probably also fun engineering problem to figure out how we can make changes to the electric grid so as to allow for the coordination and integration of these diverse and little finicky resources. I think of the problem really as a problem of coordination in 2 dimensions in space and time. And as I'll be showing you, I think it's useful to really disaggregate different aspects of the coordination problem in terms of what order of magnitude of time and distance scale are you looking at? Are you situating each different aspect of the problem? I think it's important also in the long run to think about not just mitigating the problems, the challenges introduced by renewable resources, but really to think strategically about how can we make the best of it? How can we actually leverage advantages? How can we do that in a smart manner? Now, let me say a few words about the legacy power system. And these are just transmission links in North America. Electric power systems are the largest man-made items of technology, the largest man-made artifacts. And it's really quite remarkable when you think about the fact that physically all of these components, which are, largely, well, what we're seeing here represents pieces of aluminum wire, but there's copper and, all sorts of electrical machinery, but essentially these are pieces of metal that are all somewhere physically connected. Well, somewhere they're connected by magnetic fields and transformers, but, pretty close. So you have physical interdependence all the way across these thousands of miles, which is really quite remarkable. Here are just some pictures to look at what we're talking about. It's also remarkable that most of this technology, most of this infrastructure is really essentially late 19th century technology, some early 20th century. But the idea of rotating machines for generating alternating current and conductors for conducting electricity, those are really pretty simple and old technologies, but they have been put together to make this very large and complex system. A lot of these artifacts have been around for quite a while. Just some images. Here's a distribution substation. These transformers, circuit breakers, that's all technology been around for a long time. It's not quite as bad as this, but there's some pretty funky pieces of equipment. This is at my house. Here's my meter. I don't have a smart meter yet. And so, the whole rustiness of it all, the whole funkiness is part of what we have to understand as the existing system within which we're now thinking to place very advanced electronic, smart kinds of technologies that will help us with this much more refined approach to coordination in space and time. I like to say just a word about complexity here. Really, this power system infrastructure is complex in the sense that it includes numerous individual components. They're very diverse components, as I've shown you in type. Type that includes different types of power generating resources, for instance, which we're now proposing to yet diversify more significantly with more different resources, diverse in age, behavior, how they can be controlled, what kind of information they can and can't communicate. There's another layer of complexity that doesn't even just deal with the technology, but the fact that electric power systems find themselves owned and regulated by any number of different entities, right, with different legal and commercial interests. So there's an institutional kind of negotiation as well as a technical negotiation of how does it hang together, how does it work together. You have the fact that physical disturbances propagate very quickly and can have very serious long-distance effects. The proverbial tree falling on the power line in Oregon, causing an outage in California, and other examples like that, a mistake in Cleveland causing an outage in New York City, and so forth. So this characterizes a complex system. Another way to think about a complex system is to say that it's one that no individual can fully comprehend at any given time. It's just bigger than any one human can fully account for. So by necessity, it requires different entities collaborating at different levels to make it work. In fact, my dissertation advisor, Todd Laporte, said it's a great example of a system that works in practice, but not in theory. Now, to make it work in practice takes a remarkable effort of technical and human activity, vigilance, to in fact make it so that the electric power that's generated and consumed at any given time equals so that the system stays in a kind of physical electrical balance. Now, our ability to do that right now is really limited by the existing technology, the technology that's in place, the trillion-dollar infrastructure that we have to work with, which was designed on the basis of what was imagined excuse me, what was imaginable in the early 20th century. So it's a hierarchical design that really starts from central station power plants, this hierarchical transmission system branching out into distribution systems going to customers. So the power flow really comes from the inside out, whereas the demand itself, the power demand, is actually the independent variable around which everything arranges itself, right? Traditionally in the power industry, the doctrine is that the consumer says when they want power and how much, and then we all bend over backwards to make that happen, make that possible. And that is still kind of the assumption we're working with. We're now beginning to depart from that and say, wait a minute, this is perhaps not economically an optimal way of going about it, and perhaps we would all be better off if we allowed for a little more flexibility on the demand side. But it turns out that the system as it is in place was not designed with the idea in mind that, yeah, demand is something that you could tinker with, right? Demand was supposed to be there and determine everything else. How do you make such a complex system work in real time? Well, historically, the way you make it work is by over-designing it, by building redundancy into it. That is, you have spare capacity, not just spare generation capacity, but extra room on transmission links. And you have, essentially, you make the system beefy so that when something goes wrong, there's slack built into it, that it doesn't break down. And these kinds of criteria, such as, N-1 security criteria and so forth, have been built into the physical infrastructure and into the operating culture of electric utilities. There's also a kind of physical inertia that I'll say a little more about in a little while, but that is essentially the inertia of large rotating generators that make it possible to operate the system in real time, because they will take up the slack of whatever short-term variation there is between demand and supply. Essentially, you had to have slack built into the system because there simply did not exist the technology for this kind of fine-tuned intervention controlling that we're now beginning to think about. At the heart of this is the assumption that you have to have power plants that you can turn on and off and up and down as you wish. The grid couldn't have really been built and operated without power plants that give you that flexibility. And most of those have been fossil fuel-based generation facilities. Also, hydroelectric power plants meet that standard very nicely, because assuming that you have a big enough reservoir of water, then a hydroelectric plant makes it actually very, very easy to turn a valve up and down and modulate the amount of power that you're generating very rapidly on demand without even the thermal inertia that you have in a fossil fuel burning plant. But so the flexibility in generation was absolutely essential to making the system work. Now, enter a whole new menu of options of renewable energy sources that lend themselves to electric power generation, but that don't have those traditional properties that we're used to. So on this little smorgasbord slide here, we have, a biomass power plant, which actually resembles in its operating characteristics a fossil fuel plant very nicely, except that, of course, you're a little more limited in where you can site it. It would tend to be smaller. Hydroelectric plants, there's photovoltaics, which it's starting to be really a common sight, PV on rooftops. Geothermal, an important resource in California. Solar thermal power in these concentrating troughs, and wind power. Just to show you sort of an overview of this scenario. Like I said, PV is starting to be commonplace. Tremendous growth, and really it's a question of, well, where can we think of cost-effective installations next? Carports, larger. This is actually at Sonoma State. This is on top of Salazar Hall. That's a 100-kilowatt PV system that some years ago was, very impressive. Wow, 100 kilowatts, that's a lot. That doesn't even sound like a lot anymore because so many large-scale systems are going up. The solar thermal technology is actually very interesting on the larger scale for bulk power generation. We have existing facilities in Southern California, and some more are slated to be built. Solar thermal technology, which is really about boiling water to make steam and run rotating generators. So it resembles some of the fossil fuel generation in that sense, that it deals with rotating machinery. Of course, it's limited by sunshine. It's a more efficient way to use acreage for electricity production from sunshine, more efficient than photovoltaics. Of course, there's a catch, which is that every steam generation technology requires cooling water, unless you go with dry cooling, which is something that's being negotiated as we speak. But there's tremendous land area that's theoretically available for this kind of solar thermal generation. You see, these are plants on the orders of hundreds of megawatts of capacity. They're not small. And then, of course, there's wind power, which you've all heard and read about, which can, again, come in small sizes to very large, hundreds of megawatt wind farms. Now, here's what we all also know, which is that the wind doesn't always blow when we would like it to. This is a classic slide from the California Independent System Operator saying that, gosh darn, wouldn't it be great if the wind always picked up when people turn their air conditioning on, but that doesn't tend to happen. So we have the wind in red on a particular day. This is a winter day, and the load, of course, completely out of sync with that. So this isn't going to, if this were the whole story, it wouldn't be very helpful. Of course, there's an answer to that, which is that, well, we have to combine these resources with others like pieces of a puzzle to make them fit. But the puzzle pieces aren't always convenient. Sometimes they're awkward, like this one. An even greater concern is looking at a finer time scale. And what worries the system operators is not just sort of the macro level, when does the wind tend to blow and when doesn't it, but the rapidity with which it picks up and drops off. It's the slope of this line of wind output that's really a concern. And it's a concern in terms of, when you have these very steep ramp rates here, what happens if that coincides, if it happens to coincide with electric demand picking up while the wind drops off? Then you have a very steep ramp rate in megawatts per minute or even megawatts per second, that the system operator is responsible for somehow finding a way to balance that. The power system as we know it, hasn't been really equipped with the capability to do that. There's also the super rapid short-term fluctuation in the wind output. That's a concern because it's very hard to predict and forecast and know ahead of time what you're going to have to do. So you have very little response time to deal with it. Now, in California, there's, I think, a lot of concern now about how are we going to meet the 33% renewables portfolio requirement by 2020. I'm going to go on a limb here, and I'm going to say, in my opinion, it's important to think even beyond that. Because based on what I understand about global climate change and carbon, 33% isn't even going to do it. I mean, 33% is ambitious and challenging and a little scary. But in the end, we have to look beyond that. I believe we have to look at eliminating fossil fuels, period, ultimately. That's a tall order. But so thinking strategically in the very long run about, well, how much could we do with renewables for electricity production in the United States? And let me make another aside. If you look strategically at really basically getting rid of net carbon emissions from fossil fuels, you also have to look, obviously, at transportation sector and industry. And I think what you're looking at strategically is a shift over to electrifying more energy end uses. So in a sense, the strategic problem is much bigger than looking at just how do we use a renewables portfolio to satisfy a portion of our current electric demand. Because if you're looking a century out, in my opinion, really what we have to look at is using decarbonized electricity to serve other energy needs that aren't currently met by electricity. So the problem could be much bigger. That's an aside saying, okay, looking on the big picture here, what could we do? And this is just random, not entirely random, but images of different kinds of renewable resources sprinkled across the nation. What's not an interesting constraint is overall resource availability. There is plenty of sunshine and wind to go around. Resources such as biomass and hydropower are much more constrained. Sources such as geothermal, tidal, and wave power are more locationally constrained in terms of where they're convenient to use. Solar and wind we have a lot of, and acreage is not the limiting factor. What is the limiting factor is how you coordinate them and how you put them together. So the interesting constraints are transmission infrastructure. If all your high-quality solar resources in the southwest, then you kind of have an issue with how do you get that energy to where the loads are. Same thing with the wind. If the really good, accessible, inexpensive wind resources are away from load centers, you're talking about building a lot of transmission. There are, of course, specific issues with resource location, environmental impacts. Cooling water is a big constraint because dry cooling is less efficient and more costly than standard wet cooling. But of course, because solar thermal power in particular relies only on direct and not diffuse sunshine, because you're using a mirror to focus it, so it has to come from one direction, that means it prefers a dry climate, right? The southeast is not a good climate for solar thermal power because there's too much humidity, too much diffuse sunlight. So by definition, you're looking at arid areas where cooling water is scarce, and it's going to not just involve an economic cost, but a kind of political cost for water allocation. Energy storage capacity is an interesting constraint. First of all, there's the question of if you put different resources together in a well-thought-out portfolio, how much storage do you end up needing? How much dedicated energy storage do you need? Maybe it's less than you thought. Maybe it's more than we thought. It's not obvious. And the question also of where do you place it and what kinds of storage resources do you combine? And I'll say a little bit more about that later. Overall, it's the coordination in space and time of making these resources work together that will, in my opinion, limit our ability to satisfy our energy needs from these resources. So temporal coordination means dispatching resources on a seasonal, hourly basis and short-term basis. It means having firming resources or things that will back you up. For example, if the wind stops blowing, then you need to call on something else instantaneously. Those would be the firming resources. They could be any of a number of things. They could be alternate generation resources. It could be, and we talked about this on Tuesday, it could be a well-thought-out demand response program where you would have demand response that could be actuated very quickly within a time frame of seconds to compensate for the variation in the wind power output. One of the things that Berkeley researchers are looking at. And then on an even finer time scale, there's the question of the grid stability with respect to the 60-cycle alternating current. And I may say a few more things about that later. Coordinating in space, obviously, first of all, it's the question of where do you put the resources? And that's a physical question, but also, very importantly, a political question and environmental. Transmission capacity build-out really is limited by siting, right? It's by obtaining the right-of-way for a new transmission line is a lot harder than building the physical thing. I mean, it's not cheap to build transmission lines, but the long lead time, the planning, and all the negotiation about where can you put it, that's really about, well, where do people want it? It's not about where can you technically place it. And there are more local issues that I think are kind of interesting, and depending on who, we may or may not talk about them, are coordinating protection, that is circuit breakers and such things. That becomes very important when you place smaller scale resources at the distributed level, which happens to be the case for many renewable resources because A, it's technically possible to do it. You can put photovoltaics on your rooftop, whereas you wouldn't put a small nuclear power plant in your garage. But you could have a small wind turbine, fuel cells, any number of things. So distributed generation has a great overlap with renewable generation. Another local issue is voltage regulation. That's actually a pretty tricky thing that comes up when you're looking at placing a lot of these small generators at the neighborhood level. And it's not really rocket science to make it work, except that the existing infrastructure was not built to make that work. So you have to do some modifications. And the question is, how can you make those modifications in an affordable and smart way so that it facilitates what you're trying to accomplish, that it facilitates high quality and reliability of service with a lot of contribution from renewables, and who's going to pay for it? So here's now my graphic kind of overview of how to situate these different challenges and also a way to situate research questions. I'm starting with a logarithmic time scale that goes from a microsecond to decades, which is really the whole range of time scales that you have to be thinking about when you're thinking about electric power systems. That's one thing that makes them so fascinating and interesting and difficult. Now, the reference point is 1/60th of a second, which is the cycle of alternating current. And some of the planning and operating actions that we're dealing with in the grid are actually occurring on a shorter scale and some obviously on a much longer scale. So things like circuit breakers, protective relays, operate often within a fraction of a cycle. There are certain switches that have to disconnect faster than 1/60th of a second. There are indeed switches such as the flexible AC transmission systems or FACTS that are essentially chopping up an alternating current voltage or current wave, chopping it up by throwing microscopic switches zillions of times. That's not accurate. Many thousands of times per second, much, much faster than one cycle, and thereby actively reshaping the sine wave, right? That's how we can actually control AC power flow. So that's a much, much shorter scale. Also inverters, things that produce alternating out of direct current, are chopping up and creating little sine waves at this very small time scale. Now, transmission and distribution planning is the other end of the time scale, and we're looking at not years, but decades, really. And then if we're planning strategically for reducing carbon emissions and strategically for how do we build up our renewable resource portfolio, we're really pushing that even farther out. So one way to see the impact of modernizing the grid, making it smarter and incorporating more renewable energy is really to say we're pushing out the extent of the logarithmic timescale on either end. We're talking about making it smarter faster, but we're also strategizing for longer lasting implications at the other end. The day-to-day operation happens sort of in the middle. And so the standard transactions with buying and selling power happen sort of on the hourly and daily scale. So we're talking about thousands or tens of thousands of seconds in my units. Automatic generation control, AGC, the signal that's sent to generators to turn power up or down. That happens on this 4-second scale here. And anywhere in that whole range is where our renewable resources can vary. So we have to address variations of output anywhere from seconds to days. And we will likely need different techniques and technologies to accommodate these variations on these different timescales. So these firming resources we have to look at over this range, and it's not going to be just one firming resource that can back up a wind farm. I think of a smart grid as a grid that allows you to address very short-term and very long-term kinds of planning and operation problem. That is to really make a high-functioning grid with a lot of renewable resources is going to require us to think in the very near term and the very long term. Near term meaning microseconds. Let's look at the spatial scale. Again, same deal, logarithmic scale. This is not, the previous one was 15 orders of magnitude. This is more like 6. But so geographically, you know, the California Independent System Operator has a control area on the order of hundreds of miles across. The Western systems is a little bigger than that. We're on the scale of 1,000 miles. The distribution feeder, the wires running down your street, are more on the 1 mile scale. But in fact, there's even shorter distances that become relevant when we're talking about a lot of small-scale distributed generation. Here in pink are some of the problems and concerns that show up that you're dealing with in operating the system. At the very large scale, what operators are seeing are some actually rather troubling stability issues, oscillations of a voltage magnitude and angle that can occur over very long distances that are still an important research problem, not very well understood. Some of the research going on here about implementing synchrophasers is synchrophasers are a diagnostic tool for observing those kinds of oscillations. Very important problem, very major concern for the CalISO. Wondering about, well, you know, do these oscillations actually precede outages? Do they cause them? And how is anything that we're going to do with renewables perhaps going to aggravate these oscillations? They're not caused by renewables as far as we know. They have to do with sending large amounts of power over very long distances on AC transmission lines. But knowing that doesn't really tell us, okay, how do we avoid it, make it go away? Transmission congestion, more mundane problem, simply thermal overheating. And you can only send so much power over a distance based on how much capacity you have in place. There are all the distribution kinds of issues, again, protection and voltage regulation, important ones. And then you have power quality issues that could happen on an even more local scale, such as when I run my laser jet printer, my light flickers, right? And that happens over a distance of 1 meter. And again, integrating the renewables raises concerns at all these different scales, these various scales of distance, from the question of interconnecting distant wind farms to how do you write the criteria for what does, let's say, a photovoltaic system with an inverter, how does it need to behave? If I'm going to install that in my house and connect it to the grid, what requirements does it need to meet in order to essentially be a good citizen on the electric grid? This is not obvious, and people are working on revising these standards, in fact, so that, number one, you can avoid misbehaving generation equipment, but number two, so that you can perhaps assist and leverage good behavior and supportive behavior. Because aside from being a nuisance, maybe these many small distributed generators can actually be a real asset to the grid, but we have to think carefully about how we stipulate their behavior to enable them to do that. So again, smart grid to me means thinking both about the very small and the very long scale and distance of designing and operating the grid. Now, the rest of this talk, actually what I have are just some examples of these specific coordination problems. And in my class, you'd have to buy cookies next time. Will you remember that? Bring cookies next Friday. So let me just say a couple things about these few slides, and then I'm going to skip through some slides to the end, because I have like 7 minutes, I think. That's correct. Actually, let me put it out there. Do you guys have specific points and examples that you're most interested in hearing about? I sort of laid out the framework, and there's any number of particular coordination challenges I could talk about. Yes, Dave?
Does DC transmission on a large scale change any of this?
DC transmission changes the stability problem, because when you have an AC transmission link here and another over there, and if you connect them with a DC interconnection, it could be either a long-distance DC transmission line or a kind of converter station, you basically take control of the waveform. And so you get around this problem of the angle shifting around, because you essentially, with your many switches, tell it what you want the angle to be. They're expensive to build, and you'd have to build them in a lot of places probably to deal with the problem. So that's sort of that's a trump card, I think, that we know we hold. But I think the question is, well, how much would we have to commit ourselves to putting in DC links? Yes.
Wait. Before we go into the real question and answer period, I think the issue here is, are there topics that the remaining slides should address rather than addressing specific questions? So what are our options, Sasha?
Oh, that's a good question.
Yeah.
So I could say a little bit about the stability issue and generators.
Okay, that's one.
I could say a little bit about storage.
All right, two.
I have a couple of slides about protection coordination. And then finally, how do we deal with information volume?
Is there anyone that is of particular interest to folks? We have a couple of hands back here. Just shout out the... Okay.
Do I hear storage?
It seems there's an overwhelming interest in storage.
Oh, okay, go for it.
And then we'll go into question and answer in about 5 minutes.
All right.
Great.
So here, let me show you just this picture. Is one of my favorite graphs of all time, and I snuck this from PG&E back in 1989 when I was working at their R&D department. This is an hourly load duration curve. For those, are you familiar with load duration curves? No. It's essentially a graph of how much power is being demanded in the system at any given hour, except the hours aren't organized temporally, but they're organized in order of descending demand. So you could have, 5 p.m. August 3rd here, followed by 4 p.m. July 27th, and so forth. So the hours are just the years chopped up into hours, and they're then organized by descending load, and that's the light blue curve. And this is a traditional planning tool for electric utilities, because they then think about, how do we take our generation resources and fit them in the area under the curve? Since the horizontal dimension is time and the vertical dimension is power, load in megawatts, the area is in units of energy, right? It has dimensions of energy. So essentially, if we can figure out what color crayon we use to color in the area under the load duration curve, that means we can satisfy electric energy requirements. And if we have enough resources at any given hour to be as tall as the load, that means we satisfy demand in that hour. So it becomes kind of a puzzle of how do we put resources together. And this is done traditionally. You start with base load plants that run 24/7, so your nukes might be down here, and then you have some dispatchable stuff and some expensive peak generation to fill in the top. Well, as early as 21 years ago, very forward-thinking, smart folks at PG&E said, well, let's play with this and see if we could come up with a way that we could actually meet our load duration curve with 100% renewables. And they figured out a way to do this. Now, this was not, figuring out, well, what could you legally do or what could you do economically. It was a matter of technically seeing if there was a way to match it and how much storage would you need to make it happen, because you need some storage to do it. But it actually turned out to be not very much storage, represented by those areas here where megawatt hours are being either put into storage or taken out. So I show you this just by way of saying technically it's quite feasible. Now, we're not saying this is cheap, but it was thinkable even 21 years ago. But it turns out that this resolution of modeling is actually not even enough, because here we are at the resolution of hours, from hours to years, and it turns out actually we need to work on an even shorter time scale. For one thing, there's weather. And weather forecasting also isn't on a short enough time scale right now to do the dispatch for large amounts of solar and wind. In fact, the variability is on such a short time scale that one of the things we need is better, more rapid forecasting, and we also need statistical modeling to figure out, okay, if we have a bunch of different solar and wind farms in different places, how is the effect going to combine and aggregate? That will then, again, tell us how much storage do we need to compensate for that. So the firming, and here we're putting storage in context with firming resources. You know, traditionally you have reserve generation, some of which can be called upon to ramp up and down very quickly, or regulate, that is, control the frequency, and ramp up and down even more responsively. Electric storage, I mean, I say under development, it's, you know, we have pumped hydroelectric storage. We have batteries not in use on a large scale in the grid. What's under development is really expanding electric storage capability throughout the grid. And then finally, there's demand response. There's a question of, well, can't I turn the knob and fiddle with the demand, especially if I can do it in a way that the customers don't even know it's happening. Actually, thermal storage is an important instance because the solar thermal power plants I showed you have a very important advantage over the photovoltaics in that they have a thermal inertia. If you're boiling water with, say, a hot transfer fluid like an oil, you can make a well-insulated tank and store some really hot oil for a couple of hours, or molten salt, for example. And so that gives you, in fact, some of that flexibility. So thermal storage is important. And then, of course, electric vehicles. There is a whole host of other emerging technologies not yet installed on a large scale, but that essentially should be thought of as storage technologies. The way that the system operator thinks about storage technologies, saying as if it were a person, but the way operators think about it is on what time scale does the storage become accessible or usable to you. So again, there are very different technologies and resources that would address storage needs at these different scales, and that would correspond to different services that they supply. And finally, the elephant in the room, of course, are electric vehicles that could be charged and discharged. And nobody really knows yet what the impact is going to be or how we can incentivize electric vehicle owners to do the right thing for the grid, right? Well, I mean, there's pricing, but some of it may need to happen on a very quick time scale. And so that's a big open question. There are, in addition to technical questions, questions of how do we create incentives for the right scale and sort of packaging of storage. For instance, do we think of storage at the system level by optimizing its benefits and services to the grid as a whole? Or do we think about storage as firming up a particular generation resource, which then makes it more economical or competitive to bid as a firm resource? And is it perhaps the case that even though from an engineering point of view it would seem more optimal to have storage devoted to optimizing the entire grid, in the given economic framework, is it perhaps easier to get the storage built if it becomes a tool for making individual projects competitive? I think that's all my, I'm not going to go into dynamic behavior. So that's it for the storage part, just my slides, and we can talk more. Let's do questions.
Great, thank you.
Thank you.
Okay, great.
Dave?
Thank you very much, Sasha. So let's take questions and start there with Dave.
Hi, Dave Watson, Lawrenceburg Lab.
Is the mic?
Check one.
There you go.
I had a question in the time frame of the 1 second to 60 second range. As far as the resources that are available to the system operators, do you feel that the products and that are currently in use are consistent with the needs, or do you see that the product structure and the resource structure should be revamped, and if so, how?
I wish I were qualified to answer that question. I really can't answer that question. You have to ask someone at the system operator. My sense is that they certainly wish they had more. You know, I can speak generally from an operations perspective. You know, operators deal with a very uncertain environment in which they're sort of always trying to minimize the uncertainty and make things predictable and essentially avert calamities. Operations is very different from engineering. In engineering, we think about optimizing things and being creative and opening new options. In operations, really what you want to do is close options and make sure that the thing doesn't fall apart on you, and then you're the guy who's responsible, right? That's sort of the framework in which we're living. So for the operator, of course it's desirable to have more tools, more resources to call upon. And my guess is, yeah, they could really use a lot more resources, especially projecting out to an environment where, lo and behold, there would be more uncertainty. All those jaggedy lines, that's really scary if you're the guy whose job it is to essentially make those jaggedy lines equal out into something that's equilibrated. Now, having said that, having more control options is not always a good thing, because if it could also become a pain. It could become a liability if you have things that, just because you can control them, then need to be controlled. So, and those were actually some of the later slides I was maybe going to show you. You know, what we're talking about is a very large volume of data to micromanage a lot of resources. So it can become, having the control options can become a liability if you find yourself in the position of now needing to spend the time and bandwidth to manage all these variables, especially if it's designed in such a way that it's not robust if you just leave it alone and step back from it, but if it needs to be driven all the time, right? So that's, I think, a very important caveat to consider with all of the kinds of refined control options we're talking about, to say, what does this actually mean for operators if we give them tools, but you know, we have to be careful that the tools then don't put them in the position of being in a bad place if they don't actively use them. But you know, again, I think in general the answer is yes, we need more firming resources of a variety of types that can be called upon on a shorter time signal, and demand response may very well be one of them. And different types of storage are probably also among those. Question, how does the communication flow, and how much of that communication could we keep out of the hair of the system control operators to be resolved? Yeah.
I haven't really heard many people discussing, or maybe I haven't heard of it in any event, storage related to transmission constraints. Is there any research or people doing any actual development or planning for the use of storage to overcome existing transmission constraints?
I think the caveat that we have when we look at transmission constraints is that we're looking at very large quantities of energy. You know, so if you look at a transmission line that might be able to send 1,000 megawatts, you know, over an hour's time, you know, a gigawatt hour is a lot of energy. And so I think because of the scale that you're dealing with at the transmission level, the storage simply doesn't seem as attractive or economical. My sense is that at the transmission level, storage is interesting for the micromanaging at the very short time scale to help with essentially controlling power flow and those things, but not in terms of bulk energy storage. I mean, having said that, of course, we do bulk energy storage in hydroelectric reservoirs. That's really the big one. And, you know, that's limited by how many places do you know where you can put a lot of acre-feet of water really high uphill. If you're Switzerland, you're in business, right? But in the Sierras, we only have so many places. Yes?
Hi, I was wondering if you could talk a little bit about how you see the move to this kind of management of the system changing the business models that the ISOs and the generators currently operate under, and whether the current regulatory structures that tell them what kind of business models are legal even are letting them make those adjustments.
How could I possibly skirt that question gracefully? I don't really know how to answer that. So I don't think I'll try. I'm sorry. Maybe I'll try offline.
You would have written a large part of Mark's thesis, I think, if you had been able to answer that question. Other questions? I'm sure Professor von Meier would stay around for a few minutes if someone wanted to come down front. Duncan, a question? Anyone else? Any questions from,
Yeah, right there.
from the web? Ah, can you get that one, Gaiman? Any questions coming in from the web, Anisha? No web questions. One more in the back. This will be our last question then. Oops. Push the button on the bottom, way on the bottom. Just push that in.
All right. I was wondering if you had any thoughts on how maybe distributed or decentralized combined heat and power might be able to play into a kind of changing in the spatial and the temporal timescale and energy demand.
I like that question a lot. Distributed heat, combined heat and power, especially at the distributed level, is such a no-brainer that it's sort of embarrassing that we're not doing more of it. I mean, it makes such perfect engineering sense, right? To be using heat that's waste heat in electric power generation for applications that need heat anyway. And in fact, I used to say, I grew up in West Berlin, and I used to say about East Germany that there were two things that East Germany really did well, and they were district heating and maternity leave. You know, so it is, it's really a no-brainer to do that. Distributed generation, and in particular the concept of microgrids, affords you really the ability to tailor your particular generation resources to the local loads. That is, do the loads need heat and electricity in what combination? And also, what kind of electricity do they need? What kind of power quality and reliability is appropriate? So I think that is a very important part of a way of thinking in a more refined way about not just we're providing one product and that's reliable electricity that's always on at 60.00 cycles per second, and to think about, okay, what kind of electricity do we need? Would it be AC or DC? Does the frequency matter? Could the voltage sag a little every now and then? Does your load care if it does? Does it need heat right at the same location where it needs electricity? That's a whole new framework for thinking about electric end uses. And that's being explored right now by research at Lawrence Berkeley Lab on microgrids. And I think what's actually really exciting are two things. One is the technical questions of what kinds of smart switching and coordination do you need to combine these local resources. Clearly, combined heat and power is something that technically we know how to do. But then there's also the question of how do you combine it into a local little portfolio with other things. And then there are, I think, the more challenging institutional questions and economic, and about how do you make that work on a larger scale and, again, give the right incentives. But I think without a doubt, combined heat and power is a direction that we have to go in, because we can't afford to just throw energy away anymore.
Great answers, great questions. Thank you, everyone, for coming in. Thank you, Sasha, for
Thank
a very,
you.
very interesting talk.
Thank you.